Hello everyone, hopefully you're doing well. In this video, we're going to take a look on section 8.3 or 8C or unit 8C, real population growth. In the previous video on this chapter, if for any reasons you miss it, unit A, we went over linear, growth versus exponential growth. On section, unit B, on these sections, we went over doubling time and half time. And now in these sections, we're going to continue really to study the astonishing, exponential astonishment. There are lots to learn from this. So what we're gonna do is really put the historical growth of world population into perspective, explain how the population growth rate depends on the birth rates and death rates. We're going to define carrying capacity and describe the facts that influence it, and contract models of exponential growth with logistic growth and overshoot and collapse models. So there are lots to learn from these sections. Hang on with it, especially about the whole population. We're gonna talk about it a lot. So real population growth. Perhaps the most important application of exponential growth concerns human population. From the time of the earliest humans, more than 2 million years ago, until about 100, I think 10,000 years ago, human population probably never exceed a few million. So the advent of agriculture brought about more rapid population growth. So human population is estimated to have reached about 200 million by, the year before Jesus Christ. And it's continued growing, slowly to about 500 millions of people by, I believe, 1650, 1650, yeah. So exponential growth set in with the industrial revolution. Remember the industrial revolution? We said we would never be able to feed over 1 billion of people, but thanks to industrial revolution, so our rapidly developing ability to grow food and exploit natural resources allow us to build more homes for more people. Meanwhile, improvements in medicine and health science lower death rates dramatically. In fact, world population began growing at a rate exceeding that of steady exponential growth, in which the doubling time would have remained constant. Population is estimated to have doubled from 500 million to 1 billion in about 150 years, right? Um, like from 1650 to 1800, right? Now, it then doubled again from 1 billion to 2 billions by 1922. Like from 1800 to 1922, it's a period only about 120 years. So the next doubling from 2 billions to 4 billions, you're talking about the doublings, right? Is estimated to have been complete by about, uh, you know, um, 1974. So a doubling of only 52 years. You see, we started with doubling time 150 years to 120 years. Now the next doubling from 2 to 4 billions goes only 52 years. I mean, by 1974. Now, world population is was projected to double again in 2024, recently, from, 1974 to 2024. How many years? It is only 50 years. So now, and which is true because by 2024, it was already double because we were about to 8.1 billions of people. So it's only, it takes a very short period of time, which is 50 years from now. So every 50 years, this what's gonna happen. So just imagine, very soon, how the population, the world population would be. All right. So most of all, we can see this from, there's a lot of progress about this, So to put world population growth in perspective, that's our goal, consider the following facts. So every 4 years, the world population nearly as many people as the total population of the in the US, because remember, it's about 80 millions of people per year. So the population growth world population growth by 80 millions per year. So just imagine the US population is 331 millions. So meanings you need only 4 years to fill up the whole United States. So each month, world population increased by nearly the equivalent of the population of Switzerland, while you study during the next hour and a half probably world population would increase about 10,000 people. So usually it's really hard to go about projection, but projections of future population growth have large uncertainty. Demographers often state low, intermediate, and high projections based on differing assumptions about growth rates. Like back in 2021, the United Nations intermediate projections predict that world population would reach 9.8 billion by 2050 and 10.9 billion by 21, right? 2100, like 2100, like, about 75 years from now, right? In the United States, where population is growing more slowly than the world average, the population is still expected to increase by about 80 million people over the next 40 years. So fortunately, while the absolute increase in population remains huge, these numbers indicate that the growth rate is declining. So remember, growth rate is declining. The fact this fact makes many researchers suspect that the growth rate will continue its downward trend, therefore, thereby preventing population catastrophe. So that's our expectation. So in this video, as we said, we focus on real population growth. The first thing we're gonna do is to review, starting from, review especially some of these videos covering, these sections. The first one we're gonna go over, we start, it's varying growth rates. So starting from an estimate 2021 world population of 7.8 billions. I think I make a huge mistakes here putting millions, but it's really billions. Let me fix it. Use the given growth rate to find the approximate doubling time, use the rule of 70. If for some reasons you forget the rule of 70, remember we covered it in the previous videos, and feel free to go back and see all these videos that we approximately doubling time formula, the rule of 70 for a quantity going exponentially at a rate of p% per period time. The doubling time is approximately 70 divided by p. This approximation works best for small growth rates and breaks down for growth rates of about 15%. So feel free to watch the previous video, Unit B, in this chapter, okay? So, but now, because you know it, I'm gonna go back to my exercise. So my exercise here, we said the average annual growth rate between 1850 and 1950, about 100 years, which was about 0.9%. So what they asked us to do here, use the doubling, the doubling formula. So first of all, if we go with A, we see T double. So T double, if we use the the rule of 70, so 70 over the percentage P. Remember, this is the percentage P, right? So we're gonna go with 70 over the percentage P. 9% is 0.9. We said 9%. Sorry. That give us, at this rate, it takes about 77.8 years to have a double. So under these assumptions, if we use, the same formula, again, these type of formulas, we covered them in the previous videos. Remember, you really need to go and see the new time, because at this point, we cover so much in this video. We said, um, under this assumption, the population under this assumption, remember, I do one exercise and you can do the others. Under these assumptions, the population in 2050, because they ask you what will be the populations, is 19, is no. And to predict world populations, use that world to predict population in 2050, right? Would be what? Would be, remember, we know the turbulence. So new numbers, remember when we take, because with that formula, we take new numbers, new value would be initial value. That's the formula, right? You take the initial value, you multiply it by 2, okay? With with we take the time, small time, over the t double. So what is t then? Remember, if we want to find t, we need to subtract, because since starting from 2021, so 2021 from 1950, all right? The 1950, 2021 would give you what? You need to find that number. So if I take a calculator, right? If we go, what is that t? We go 21, no, 2050 to from 2021. So t would be 2050 minus 2021. What would be t? If I take a calculator, 250 minus 2021, because you need to find this t, okay, that would be 29. Remember, the small t after a time t, all right, and we know the time t, because from 2021 to 2050, that make it 29 years. So we go, that new value here, what is the new value? The new value, initial value is from 21 is 7.8 times 2 power 29 over the doubling time is 77.8. Okay, 77.8. Now, how long is gonna take? Of course, this population by 2050 would be 10.1 billions. Okay, people by 2050, right? Up 2050. Okay, so that's an examples. And you can use, we can do any of these of this exercise. The next one, what they ask you, if we want to do either A or B. If we want, you know what? Let's do C. If we go C, Okay. The average annual growth rate between 1970 and 2000, okay, which was about 1.6%. Okay, so we said T double. First of all, you need to find the doubling time. T double would be, remember, if you use the rule of 70, you already know what is this one. That's P. Okay, 70 over 1.6. How long it would take for this population to double? 43.8 years. Now, under this assumption, the population in 2050, so the population of 2050, remember our goal is to do starting from an estimate of 2021. We're still doing 2021. The population from 2050 would be the initial value, would be the initial value 7.8 times 2. T, remember T doesn't change because 2050 minus 2021, yeah, make it 29 years over the doubling time, 43.8. So the population of 2050, I put 25, so sorry. Okay. 2050 would be, when you do all these computations, it would be 12, you know, the population by 2050 would be 12.3 billions. Okay. So we answered these questions. I think we're ready to move forward with other questions for now. Let's go with the definitions. Of course, we have so much to cover in this one, but it's important to talk about the overall growth. So, what determines the growth rate exactly? So, the world population growth is simply the difference between the birth rate and the death rate, right? If you know birth rate and you know death rate, you can find the world population growth rates, right? That's very important. Birth rates has dropped rapidly throughout the world during the past 60 years. You know that, right? It's very important to remember that worldwide birth rates have never been, the same period that has, seen the largest population growth is history. I would say like maybe a lot of years ago, 60 years ago, I would say. Worldwide birth rates have never been lower than they are today. Today's rapid population growth comes from the fact that death rates have fallen even more dramatically. So because the only reasons we have so many people, it's not because a lot of people have been born, but it's because people don't die very quick. So overall growth rate, the overall growth population growth rate is the difference between birth rate and the death rate. So that's right there. Okay. I don't know if you have that. So for us, what's very important here, I think we covered it in section in unit 8A. Exponential growth cannot continue indefinitely because human population cannot continue to grow much longer at its current rate because with elbow to elbow over the entire earth in just a few centuries. Theoretically, models of population growth therefore assume that human population is ultimately limited by human carrying capacity. That's very important. Okay. So that's the number of people that F can support. So for any particular species in a given environment, the carrying capacity is the maximum sustainable population that is the largest population the environment can support for an extended periods of time. So what we mean by that, you cannot have a populations that grows indefinitely. Remember, this is that's the growth, exponential growth. Remember, if I don't do it very well, but you can do like this is the exponential growth, right? But we don't want this. Okay. So at some point, there should be some type of carrying capacity. Let's say if the M is somewhere here, this is the maximum we can date. Even though for some reasons you might have a population that grows you know, but reach the capacity. The same way, people died. So we can go around this M that's we call carrying capacity. So if we call M the carrying capacity, that may happen. We have so many examples we can see that way, but you know what? So we know, suppose I call M carrying capacity. Okay? Very important to put it that way. Okay? Very important to put it that way. So we can do that. Okay. All right. Now that we know what it is, okay, let's try with an examples. In these particular examples, I believe we give you a tables. In this table, we talk about birth and death rates. The following tables give the birth and death rates for four countries in 3 different years. So you have, the four countries in 3 different years. So 1980, 1995, and also 2019. So we have birth rates on the left and death rates on the right for Afghanistan, China, and we have it for Afghanistan, China, and Russia, and the United States of America. So you see, death per thousand number the death per thousand in America in 2019 is 9. So it's like second largest after Russia. So Afghanistan is doing way better than we do here in terms of the number of people died, per thousand. But in terms of uh, death birth rates, America and China's doing, Russia is doing way better than Afghanistan in all three, right? But that's not the problems here. The problems, they ask us to use this table to answer the following questions. So find your country's net population growth rate due to birth and death rates, neglect immigration. If in 1980, 1995 and 2000, not 2016. I think the problem should be 2000. We don't have 2016. I think I might made a mistake putting 2016. I'm gonna check with that anyway. So let's go with that one first. That's very important to verify this. In these problems, okay, so we can give me a few. Okay, in these problems, the first thing to do, the growth rate. The growth rate in 1980, the growth rate in 1980 for Afghanistan. What is the growth rate? 1980. This is the two. Remember, growth rate, we said growth rate. We said it's birth rate minus death rate. That's very simple. So when they ask you for all of them, let's say Afghanistan. If you do Afghanistan, no, Afghanistan. If we do that, um, we can do each of them separately. So growth rate will be birth rate 51.8 minus 24.1. We just subtract, so that would be 27.7 per 1,000 people. Right? That's what we said. Remember, we are doing Afghanistan. So, I mean, that was for 1980. 1980. So, if we do 1995, still for Afghanistan, growth rate, you just need to do the growth rate for each time, that would be 52.6 minus 20.1, So 52.6 minus 20.1, it gives you 32.5 per 1,000. So if we do 2019, okay, we're gonna do 2019 as it is. I don't know why I said 16, so it should be 19. Growth rate, okay. 2019, we have 32 minus 6. So 32 minus 6 is only 26. As you can see, you see the decline. I mean, not really decline. 1980 was like 27. Now we goes up to 32. Now we go back to 26. Okay. So I take one example because we said for the following, find the country's net worth growth for due to births and rates. So I'm gonna do only, let's do only Afghanistan for now. That's a goal. We're gonna do only Afghanistan for now because remember we said do it for Afghanistan. That's what we said down there. We said these questions we need to repeat it, answer it for Afghanistan, answer it for China, answer it for Russia, and answer it for United States. I'm gonna do only Afghanistan, and I would let you do for the other ones. Okay. So now, part B, we're doing only Afghanistan. So whatever I do here for Afghanistan, you must do it also for China and Russia and United States. Let's answer part B because this is A. Whatever I do here is A. How about B? Describe in words the general trend in the country's population growth rate. Based on this trend, predict how the country's population will change over the next 20 years. Do you think your prediction is reliable? So the next 20 years from 2019 to 2039, that make it 20 years, right? Um, the birth rate and death rate both decline overall. So as you can see, you go 51, 52, now you drop to 32. So it's really dropped, decline. You go death rate 24, 20, then you drop to 6. Birth rate and death rate both decline overall, which results in a constant positive growth rate. So I'm not writing, I'm hoping you can write what I said. This implies a growth population in these trends, if these trends continue, we can expect an increasing population in Afghanistan, right? Because people don't die, people don't die very quick. If this one continue, we would expect an increasing population in Afghanistan, because there are so many factors that influence the growth rate of a country. It would be unwise to put much faith in these predictions 20 years, right? So we cannot say, oh, you know what, in 20 years, this is what's going to happen. No, you cannot because there's a lot of things that might change. There are a lot of factors, but we know if this trend continue this way, there would be a big increase, big increase. Predict a big increase. Predict increase in population. Right? That's just an example. But usually I said the birth rates and death rates both decline overall, which results in a constant positive growth rate. So this implies a growing population, right? If these trends continue, we can expect an increase in population in Afghanistan, right? Because there are so many factors that influence the growth rates of a country, right? So hoping this one help, but please, you do for China, Russia, and the United States, hoping this one help because our next topics would be definitely logistic growth rates. So because that's something you need to pay attention from now as we would continue studied logistic equations, through differential equations, sometimes after a few other math courses. So two important models of for population approaching the carrying capacity are a gradual leveling off, known as logistic growth, and also a rapid increase followed by a rapid decrease, known as overshoot, overshoot or collapse. So we're gonna investigate both of them very quick and see how you would see it. So we said logistic growth models assume that the population growth rate gradually decreases as the population approaches the carrying capacity. So that's what we're gonna do here. When the population is small relative to carrying capacity, logistic growth is exponential with a fractional growth rate close to the base growth rate, R. As the population approaches the carrying capacity, the logistic growth rate approaches zero. So the fractional logistic growth rate at any particular time depends on the population at that time, the carrying capacity, and the base rate, the growth rate R. So what we said by that, even though this is the model for a logistic, so on a XY plane. So as I said, so this is the exponential growth. So if we have exponential, it's gonna keep growing like this. That's exponential, right? Exponential growth. Now, we said, suppose we have a carrying capacity. Let's suppose our carrying capacity is that line. Carrying capacity. So we're gonna say carrying capacity. Okay. We call the carrying capacity sometimes M, right? Now the logistic growth, because remember the exponential growth, when the population is much less than the carrying capacity, logistic growth looks like an exponential growth, right? But you know, if logistic growth level off as the population approaches the carrying capacity, look what happened. We may have something like this is the okay. I'm gonna call this one. That's the logistic, right? Not the logistic growth. We don't overlap the carrying capacity. That's very important. So contrast logics and this graph contrast contrast logistic and exponential growth for the same base growth. Um, the same base growth rate R. In the exponential case, the growth rate equals R all the time. In the logistic case, the growth rate starts out equal to R, so the logistic curve and the exponential curve looks like the same. I mean, like the same at early times, but As time progresses, the logistic growth rate decreases and approaches zero, and the population levels over the carrying capacity. So that's what we try to explain this. I know we tells you there are two models that we need to see. Is logistic growth and overshoot and collapse, right? So we're gonna now that's the logistic growth rate. Logistic growth rate equal the rate times one minus population over the carrying capacity. That's a formula. Please write it somewhere. It's very important to remember it. But exponential growth at some point is this one, as we said. I was trying to explain, I even forgot I put that graph here, but I was trying to explain it using this graph. But you know what? In the exponential growth, as we said, the growth rate stay equal to R all the times. In the logistic case, the growth, okay, rate starts out equal to R, and as time progresses, the growth rate becomes ever smaller than R until it finally reaches zero as the population levels out at the carrying capacity. Very important. Now, we'd like to go over a few examples very quick. All right. One of the examples we want to cover here, consider a population. That's what we're gonna do. Consider a population that begins to grow at a base of 4.0% per year and then follows a logistic growth pattern. If the carrying capacity is 60 millions, find the actual factual growth with when the population is 10 millions, 30 millions, and 50 millions. So they ask us to do for 10 millions first, then we do for 30 millions, and we're gonna continue to do it and so on. So I'm gonna do the 10 millions and probably 30 millions, but I'll leave the rest for you. First of all, what they asked me to do in this exercise, they said, find the actual fractional growth rate. Okay. So we know the logistic growth rate equal, because this formula here, logistic growth rate equal, if you take the same formula, you know what? I'm not gonna write it. How about I just do copy paste? I'm hoping I can do that, right? Copy and I can do paste. Right, it's working. So let's erase this. Okay, this is the formula we're gonna use. Okay, let's use this formula right there. And now we can answer the questions. The first questions, when the population is 10 millions, okay, sorry about that. When the population is 10 millions, we're gonna say logistic growth rate. So logistic. No, I don't need to do all of this. I'm gonna be lazy, okay? Let's be lazy. I'm gonna just go and copy paste. Okay. We're gonna try to be lazy. So that would be, what is the rate, please? The rate is 4%. So we're gonna set 4%, 4 over 100 or 0.04 times 1 minus, what is the population we talked about? 10 millions. Over the carrying capacity. They said if the carrying capacity is 60 millions, voila. Then all you need to do, grab your calculator it would be 3.3%, right? So that's what we're gonna find. So the same way, if you do this population, I'm gonna try to do two of them. You know, when pop is 30 millions, right? And you're gonna do the same for that. If it's 30 millions, all you need to do is if it's 30 millions, what we're gonna do, we're gonna plug the rate 4% times 1 minus 30 over 60. Okay? And that's what give us for 30 millions, it's approximately 2.2%. Right? And I left the 50 millions for you. Remember, I do something, you do something else, because as we said, in this case, there are two important models for population approaching the carrying capacity. One is the logistic growth that has a gradual leveling off, and second of all, a rapid increase followed by rapid decrease, also known as overshoot and collapse. So the overshoot and collapse is very important. Uh, Logistic model assumes that the growth rate automatically adjusts as the population approaches the carrying capacity. However, because of the astonishing rate of exponential growth, real populations often increase beyond carrying capacity in a relatively short period of time. This phenomenon is called overshoot. So, to make it short, we said the phenomenon where a real population increase beyond the carrying capacity in a relatively short period of time is overshoot. If the overshoot is substantial, okay, very important. You said when a population overshoots carrying capacity of its environment, the decrease in the population is inevitable. So, meaning if the overshoot is substantial, the decrease, there would be, kind of a rapid and severe decrease in the population can occur. That phenomenon is called a collapse. That's very important. You can see this graph. Remember, there would be that carrying capacity that's supposed to go somewhere here. So overshoot is because it goes up over the carrying capacity. Now, after that, something happened, it's collapsed. So very important. Think about it. The concept of carrying capacity can apply to any localized environment. Remember that. Consider the decline of past civilizations such as the ancient Greeks, Romans, Maya, or ancestral Pueblans, right? There's an overshoot or collapse model describe the fall of any of these or other civilizations. So we can work around this. There's a lot to learn about carrying capacity. I know for carrying capacity, we can read so much about it. I would strongly advise you to go over and read it because given that human population cannot grow exponentially forever, we talked about it before, logistic growth is clearly preferable to overshoot or collapse. Logistic growth means a sustainable future population, while overshoot and collapse might mean the end of our civilization. We don't want this to happen, right? Uh, you know, so the most fundamental questions about population growth, therefore, concerns the carrying capacity. So I think we went over a few examples here. Any estimate of carrying capacity is subject to great uncertainty for at least four important reasons. So we can see so many reasons, but some of them are here you know, very important. The carrying capacity First reasons, the carrying capacity depends on consumption of resources such as energy, right? However, different countries consume at very different rates. For example, the carrying capacity is much lower if we assume that the growing population would consume energy at the US average rate rather than the Japanese average rate, which is about half the US rate. So it all depends where which country. However, different countries consume different rates, right? The second important reasons, the carrying capacity depends on assumptions about the environmental impact of the average person. So a larger average impact on the environment means a lower carrying capacity. And if we go with a third one, because as I said, there are several of these, the carrying capacity can change with both human technology and environments, right? Like for example, estimate the carrying capacity typically consider the availability of fresh water. However, if we can develop new sources of energy, such as fusion, it may be possible for nearly unlimited amounts of fresh water to be obtained through the desalinization, right, of seawater. Conservatively, global warming is altering the environment and might reduce our ability to grow food, thereby lowering the carrying capacity. There's a lot we can learn on this. But the fourth important reasons, if uh, if we could account for the many individuals factor in the carrying capacities, such as food productions, energy, and pollutions, you know, Earth is such a complex system that precisely predicting the carrying capacity may well be impossible. For example, no one can predict whether or how much the loss of rainforest species affect the carrying capacity. So it's really, it all depends on what we're doing. So, what we're planning on doing here, you can see difficulties of population predictions. In many cases, it's very difficult to predict. The history of attempts to guess the carrying capacity of Earth is full of incorrect predictions. So, among the most famous was that made by English economist Thomas his name is it's right there, Thomas Malthus, right? Um, I believe, yeah, he was the one doing this. Among the most famous is that guy, I think 1764, 1834. So because in 1978, paper entitled An Essay of Principle of Populations as it affects the future improvement of society. This guy argued that food production would not be able to keep up with the rapidly growing population of Europe and America. He concluded that mass starvation would soon hit these continents. His prediction did not come true, primarily because advances in technology did allow food production to keep pace with population growth, so which is really false, right? But at that time when he said that, it was really false. So you can see how the population grew over the years, from 750 to 2017 so far. That's how we put it together. So, um, an examples of mathematical models, so very important, we can see that. These examples offers an important lessons about mathematical models. So they are useful for gaining insight on the process being models. However, mathematical models can be used to predict future change only when the process are relatively simple. For example, it's easy to use mathematical modeling to predict the path of a spaceship because the law of gravity is relatively simple. But the growth of human population is such a complex phenomenon that we have little hope of ever being able to predict its reliability. So that's very important. And we're gonna just go over one more examples to conclude. This is really similar to the previous examples, but they said consider a population that begins growing exponentially at the base rate of 6% per year and then follows a logistic growth pattern. Okay. If the carrying capacity, we still have a carrying capacity of 80 million. So find the actual growth. So it's exactly the same thing we did before with the previous examples. You know, if you have a populations, if populations is 10 millions, right? I think you can still use the same formula we have here to do it. We know the rate. What is the rate? 6.0%. 1 minus 10 millions is exactly the same exercise over 80 millions, right? If you can do that, because that's the formula. So that gives you 5.25%. So yes, use this to answer any questions in the homework and also get ready for anything. You know, we're done with this chapter, even though there are more sections, but that's not really related to what we intend to study in this class. In a different video, we're going to come back for the next chapter. You have a good day. Let me know if you have any questions. Take care.